From this lecture onwards, we come to the last part of this course called the physical properties of crystals, and we are going to discuss, to begin with, what kind of physical properties we are going to talk about and how these physical properties and symmetry relate to each other. But before I begin, let me give you a couple of references which could be quite useful, and these are the references that I have also given as part of this course. So, there is a book Physical Properties of Crystals, authored by J.F. Nye. This is quite a comprehensive book and also a fairly old book. A more recent book is titled Tensor Properties of Solids, authored by Richard F. Tinder. So, these are some books that you can refer to for this part of the course. Now, first let us look at how do I define any property. So, it has to be defined by a relation between some measurable quantities. Let us take a few examples. Example 1 is density. So, a density of a crystal or density of a solid is a function of mass of the solid and its volume. Let us take a second example. A second example is electrical conductivity. Now, electrical conductivity property can be defined as a relation between the electric field and the current flux. So, if I denote the electric field by E, so this is the electric field, and by flux, let me define this as flux J. So, this is a current flux, and let us take some other examples. Other examples could be thermal conductivity. Now, this is a relation between heat flow and temperature gradient. Could be crystal polarization on application of a mechanical stress, and the property that relates the polarization to mechanical stress is piezoelectricity. Another example could be relating deformation of a solid to applied mechanical stress, and here the property that concerns us is the elasticity of the solid. So, these are all probably most of the terms you would have heard. Let us say if I look at example 1, how does it differ from the other examples I have given? Example 1 is a density property of a solid. Now, here the difference that is going to be come about is that there can be no reference to a direction in a crystal, and it can only be a single number. But on the other hand, if I look at electrical conductivity, now electrical conductivity in a crystal can be different in different crystallographic directions in a solid. So, we have to therefore, for direction and magnitude comes in play here. And if the electrical conductivity is different in different directions, then we say for that particular crystal or a solid, it is anisotropic with reference to electrical conductivity. Similar is the case here also. Other examples that I have given also require specification of direction. Now, how to specify a physical property? This is where we will bring in the concept of a tensor, and that is why many of these properties are also referred to as tensor properties. We will understand what is a tensor as we go along, but let me give an example of a tensor which many of you may have learned. If you had done a course on mechanics or mechanical behavior of materials, you would have come across an idea of a tensor. So, an example is what is called as the stress tensor. How do you specify a state of stress at a point in a solid? So, it is specified by a stress tensor. So, at any point I can draw a small cube and let us give it Cartesian coordinates, and let me give, instead of specifying the axes as x, y, z, I am going to specify the axes as x1, x2 and x3, and we will follow these axis system throughout the rest of the lectures, x1 being the x axis, x2 being the y axis, x3 being the z axis. Then we can define a normal stress. Since this is acting on the x3 plane, we call this as sigma 3,3. Then I can define the shear stresses sigma 3,1 acting on the plane x3 in the direction of x1, sigma 3,2 similarly, and you can imagine that I can also define a normal stress on the x2 face sigma 2,2, sigma 2,3 and sigma 2,1, and finally one can also define normal stress on the x1 face, as sigma 11, sigma 12 and sigma 13. All of this. So, I have a total of 9 components of a stress state that I have defined here. They can all be put in a kind of a matrix as sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32 and sigma 33. This is a tensor, and more specifically it is a tensor of second rank. So, let me just give a very quick definition of a tensor and second rank. After all, this tensor looks like a matrix, but it is in a way different from the matrix. Its representation is in the form of a matrix, but a tensor follows a transformation law. If I change my coordinate axes, then how does the components of the stress tensor changes? It follows a very specific transformation law for that. Now, let us say for any tensor, if R is the rank of a tensor, then the number of components of the tensor is given by the dimension in which we are operating. We are operating in 3 dimensions. So, 3 to power r. Now, this stress tensor has 9 components. So, this has to be 9, which means the rank of the stress tensor becomes 2, and that is why it is called a tensor of second rank. Now, as we go along, we will find that there can be also tensors of a lower rank as well as tensors of higher ranks. Let's take a look at another quantity that with which we are very familiar with, which is a vector. Examples of vectors could be a mechanical force, temperature gradient, moment of a magnetic dipole. Now, all of these can be specified by 3 components. So, if this vector I denote it as P, then it will have 3 components, P1, P2, P3 along our reference axes x1, x2 and x3. Now, if I think in terms of a tensor, I say this is also a tensor. So, number of components here we are operating in 3 dimensional space, 3 to power r, and this should be 3, and hence the rank is 1. So, a vector is a tensor of rank 1. Let us look at a scalar now. Example of this, one of the examples we have already seen, density, temperature of a body, and you can find a host of other scalars. So, in all of these quantities, it is meaningless to define or specify these quantities with reference to a direction. What will be its rank? Well, number of components are only 1, 3 to power r, which implies that the rank r is 0. So, scalar can be considered as a tensor of rank 0. So, I have scalar where only one value need to be specified. I have a vector where I have to specify multiple values. I have tensors of higher ranks like the tensor of second rank. Multiple values have to be specified in these cases. Now, how can we relate all of this stuff? So, we will just take now some very specific examples. One way to look at a property is that the property will describe how a material will respond due to an action, due to a change in external conditions. So, let us say response of a solid to a change in external conditions, and this response would have to be defined or can be described by a particular property. So, imagine that the external condition can be described by a vector, the response can be described by a vector. So, there is a what I can call there is a cause vector. For example, a force that is getting applied or a electric field that is being applied. So, that becomes a cause vector. In a very general sense, we can regard this as some kind of a force, and let me call this vector in general as P. Now, we have an effect vector. So, this is the response, the effect vector is the response. Again, in a general sense, one could consider this as some kind of a displacement, and let me call this vector as Q. Now, this displacement or the effect vector Q is related to the cause vector P linearly through a property described by T. We can make this definition much more general by calling P and Q as some kind of tensors. So, they could be of in this case, if I call this as vectors, so P and Q are tensors of rank 1. So, let us just keep it like this. So, P and Q are tensors of rank 1 or simply a vector. Then T would necessarily have to be a tensor of second rank. So, this is a very specific situation I have taken, and a large number of physical properties can be represented by tensors of rank 2. So, let us take some examples. First example is essentially coming from Ohm's law on electrical conductivity, and one can write the flux, relate this to the electric field, both of them being vectors, through a tensor sigma. Now, please note that the symbol sigma is used as an electrical conductivity symbol as well as for a stress symbol. So, here depending on the context, we could be using similar symbols here and there. Another example coming from Hooke's law. Is the strain related to the applied stress through elastic property tensor. Here I am just call it as, and third example could be if I apply a magnetic field that develops a magnetization and it is related through the tensor magnetic susceptibility. All of these, one should note that there is a linear dependence. And in general, this linear dependence is valid for small cause vectors, small responses. So, we can that this is valid for generally valid for small values of the effect vector, which we have also been calling as displacement, so small displacements. If I let us say plot magnetization versus the magnetic field, I might get a curve something like this. So, it is linear out here, later it becomes non-linear and eventually it saturates. So, let us come back to this relation in general for properties which are going to be represented by tensors of second rank. So, I can write down this in terms of different components. So, let me elaborate this equation a bit in the next lecture. Thank you.